Welcome to the Introduction to Traffic Flow Theory, Part 1. We're going to be talking about basic measurements in traffic flow. The objective will be to introduce the basic traffic flow measurements and some key definitions. We're going to focus on units and dimensional analysis, and we're going to think about the relationship between these different measures and observe how these relationships lead to the formation of a theory. Finally, we'll wrap up by comparing this theory to some real measured data. Just as a reminder, dimensional analysis is a nice way to keep track of units when dealing with traffic variables. This is applicable in many fields of study. You probably first came across this in chemistry. This example shows how you can calculate the capacity of a rail line if you know that there are 6 trains per hour with 10 cars per train and 50 passengers in each car. You can cross multiply to obtain the result of the capacity being 3,000 passengers per hour. You can see that when you cross multiply, these units will cancel out, leaving you passengers over hour. Similarly, you can use dimensional analysis to convert from one set of units to another, so you can easily convert 60 miles per hour, for example. 1 mile is equivalent to 5,280 feet. 1 foot is equivalent to 12 inches. 1 inch is equivalent to 2.54 centimeters. 1 meter is equivalent to 100 centimeters. And 1 kilometer is equivalent to 1,000 meters. If you cross multiply in this way, the units will cancel out diagonally, leaving you with kilometers divided by hours. And if you multiply these numbers and divide, you obtain 96.6 kilometers per hour. The other thing I like to remind students in transportation is we'll often deal with slope. And slope, of course, is if you draw a triangle, the slope of the hypotenuse is rise over run. So if you're connecting 2 points, for example, this point to this point, the slope of the vector connecting those 2 points is just the rise over the run. We'll use that later. Some basic measurements in traffic flow. I want you to visualize yourself standing out in the field at the side of a road. And these vehicles could be trucks, cars. If you're at an airport on the side of a runway, they could be planes. These could be bicycles, motorcycles, even pedestrians. But I'm going to use this little red shape to represent a generic vehicle. So imagine you're standing at a point and you establish a line across the road, and all you're doing is you're keeping track of the exact time from the clock that each vehicle passes. So you are fixated on this line across this road, and you're recording the time that the nose of each vehicle crosses that line. So you'll stand out there and do this over a specific time interval. In transportation, we typically count for 15 minutes or for 1 hour or for 1 day, for 1 month, for 1 year. Quite often we do this using automatic sensors, but I'd like you just to visualize that you're doing this yourself. Now all you do is write down the times that each vehicle passes by so that you basically have a list of vehicle number and passage time. And this can easily, in Excel or even by hand, be converted to this graph where you can see that time is on the x-axis and vehicle number is on the y-axis. So you're simply putting a little vertical line each time a vehicle arrives. So that means that this is a function of cumulative vehicle arrival. The function increases by an integer, 1, each time a vehicle passes. So this diagram now gives you a full picture of the passage of vehicles at this point on the side of the road. So this cumulative arrival curve is something that's used in transportation quite often. And the stair-step shape is a function of the fact that each vehicle represents an integer count. So believe it or not, there's a lot you can do with that small list of vehicles. We can take the total number, which was 9 vehicles, and the counting occurred here during a 15-minute period from 9 o'clock to 9:15. So you can divide the number counted by the time interval, vehicles per minute, We usually express this particular parameter in units of vehicles per hour, so you can convert using dimensional analysis. So 9 vehicles in 15 minutes is equivalent to 36 vehicles per hour. And generally speaking, in the world of civil engineering and the world of science, is that when we count numbers of things per unit time, we call that flow. So traffic flow is simply the number of vehicles passing a particular point per time. And flow is something that we see in other branches of civil engineering, like in hydraulics and hydrology as well. So the average flow that we calculated of 36 vehicles per hour is really represented by this straight line, which starts at time equals 9 o'clock and ends at the at height 9 at 9:15. So we can approximate the vehicle flow that's happening during this 15-minute period with the straight line. So this is the average flow shown by this gray triangle, whereas the actual flow fluctuated a little bit. So it kind of went up and down a bit according to the tip of the green dots. But in this case, the average flow, 36 vehicles per hour, is shown by the straight gray line. So that's flow. So we're still standing at one point. And think about maybe that point is actually a bus stop. So we would want to count the number of buses per unit time. In public transportation, we refer to that as frequency. So 4 buses per hour or 36 buses per hour would be what we would call the frequency. In public transportation and in other forms of transportation, we're often interested in the actual or average time between buses, and you can think about why that might be. Why might you care how much time passes on average between the arrival of a bus or a train or even an airplane? So the number of buses per unit time we call frequency, and if we think about here the time divided by the number of buses, that is the inverse of frequency, just the inverse of this equation here. So 1 over the frequency we call headway. So the time between buses is called the headway. So 4 buses per hour, what would the headway be there? Actually, it would be 15 minutes. So you can think about the relationship between frequency and headway when considering public transportation. So we've seen a few parameters so far. We'll abbreviate flow with the letter Q. Flow is measured in units of vehicles per time, and I've abbreviated that with the number sign per time. Frequency is the number of vehicles per time. It's the same. Headway is the inverse of frequency, which is the time per vehicle. It's also the inverse of flow. So just in equation form down here, flow Q equals N over T. So that's the number of things divided by time. The total travel time. So if you are counting over a period of time, the headways of vehicles that are passing by, the sum of all those headways would be equal to the total time interval. So if you have a 1-hour period and you count 4 buses with 15-minute headways, the sum of 4 15-minute periods equals 1 hour. And then finally, the relationship between the two, you can see this relationship. Flow is just N divided by the sum of the headways. Okay, so that's the basics. So you can also measure speed. So we call point speed something you might measure using a radar or LiDAR gun. So if you've been the unfortunate recipient of a speeding ticket, perhaps the police officer who observed you is using a radar gun and measured your speed. So speeds are measured for enforcement purposes using radar or LiDAR guns. And if you're taking CE 322 here at Cal Poly, you'll get some experience with that. So speed, of course, we remember from, I think, at least I remember it from elementary school, learning that rate times time equals distance. Speed will abbreviate with the letter V, and speed is just the distance traveled divided by time. And here in the US, we usually abbreviate that in miles per hour. Of course, speed can be measured in other ways. The convention in transportation is in the US is to do miles per hour. In most other countries, it's kilometers per hour. So when you're talking about speed in transportation, even if you're measuring something in miles per minute or miles per second or any other distance divided by any other units, it's best to convert to miles per hour. So think about it, whether you might want to collect a set of vehicle speeds over a time interval. So you might stand or sit by the side of the road with a radar gun and observe a number of vehicles during a 15-minute period, measure their speeds, keep track of those speeds. And then if you take the arithmetic mean of those speeds, you've measured something we call in transportation called the time mean speed, or the TMS. So that's only valid for that one point and over that one particular time interval. So in equation form here, you sum up the speeds that you measure and you divide by the number of observations that you have. This is also if you have travel times. The equivalent way to do this, travel times of vehicles traveling a particular distance d. It's the same procedure where you take the sum of the distance divided by the individual travel time and then divide that summation by the number of observations. So remember that the time mean speed is a point measure, and this will be important in a minute. So we're moving away from point measures, flow and headway and frequency and time mean speed or point measures. We're going to now consider a section of a road, and on this illustration here, just imagine that this is a 1 mile section of roadway. This particular roadway has 6 vehicles on it, and imagine that I've taken an aerial photograph. So if you zoom in on an aerial photograph, you'll quite often see vehicles on the roadway, and we're just taking a hypothetical 1 mile section, and we've counted the number of vehicles at this particular moment on this section, and we can come up with a relationship here, the number of vehicles divided by the length of the section. In this case, it's 6 vehicles divided by 1 mile, 6 vehicles per mile, and in transportation we call that density. So how densely occupied is this roadway section? I mean, a 1 mile section with only 6 vehicles on it is not very dense. Usually if you're stuck in a traffic jam, the density would be much, much higher. So we can also think about what, if we know the density, the average density, we can think about what the average distance between vehicles might be on this segment. So the total distance is 1 mile. How much of that 1 mile stretch is on average devoted to each particular vehicle? So you take 1 mile divided by the number of vehicles, 6 vehicles, and we'd like to convert that into feet per vehicle, so 5,280 feet equivalent to 1 mile. So this means that each vehicle is allocated an average of 880 feet. So that's something that we call the spacing. So now imagine that we take 2 photos at 2 different times, time 1 and time 2. And we know what the time interval might be. Maybe they're taken 1 minute apart. So if we look at a particular vehicle, we'll call this vehicle number 1, and we look at its position along the roadway. We call that X1. Assuming it's a straight roadway, it's pretty straightforward. And then at time 2, we see, well, how far has that vehicle moved? It's moved a little bit. It's now at location X2. So if we know the distance that a vehicle has traveled, and we know the time that it took to do that, we can calculate the speed, because we remember that the speed is just the distance over time. So in equation form, the speed of vehicle 1 is just x1 minus x2, that's the vertical distance here that it's traveled, divided by t2 minus t1, that's the horizontal distance for this triangle. I told you we'd be using triangles for our analysis. So if you collect a bunch of speeds in this particular way, such that you know the actual speed over space of each vehicle on the roadway, and then if you compute the mean of that, you've measured what we call the space mean speed for this particular segment over a time interval. So the the space mean speed is the sum of the spatial speed that we've measured here divided by the total number in the sample. We also call this the harmonic mean, and so if you know the distance that each vehicle has traveled and the time that it's taken to do so, you can sum the inverse of that, divide that by the number in the sample, and then take the inverse of that. That's the equivalent of multiplying the distance traveled by the number divided by the summation of the travel times. So sometimes people get confused about time mean speed and space mean speed, so I just want to take a moment to remind you that the time mean speed is something that you measure at one point, and you collect a bunch of those speeds and you take the average, and you can obtain the time mean speed. Space mean speed is defined as the speeds of all vehicles occupying a given highway segment averaged over time. Also, we call this the harmonic mean. And as we'll see later, time mean speed is always greater than or equal to the space mean speed. So I should say, is greater than or equal to the space mean speed. So now putting this together, we've come up with quite a few different parameters. We've talked about the flow, the frequency, the headway. We've talked about the density and the spacing, and in this case, the headway is the inverse of the flow. You can see from the units. Spacing is the inverse of the density. And we've talked about speed. We have not talked yet about pace, but pace is just the inverse of speed, which is the time it takes to travel a particular distance. So here we've got 7 different parameters that make up the fundamentals of traffic flow theory. I'm going to zoom in on 3 of them, flow, density, and speed. And so we're going to collapse this a little bit. And so all I'm showing here are those 3 parameters and their units. Flow is the number per unit time, density is the number per distance, and speed is the distance per time. So on the right-hand side, can you see that there's a relationship between those units? So I hope you can. So what I think we can conclude is that using dimensional analysis, the number per time is the same as the number per distance multiplied by distance per time, because the x's here will cancel out. So this is actually quite an important relationship. Of course, this is flow, or Q, this is K, or density, and this is V, or speed. So we can say that flow equals density times speed, and we've just derived that using the units. But it is an important theory, and it's known as the fundamental relationship of traffic flow, or the fundamental traffic flow theory, that is the relationship between flow, density, and speed. So we're going to take a breath for a second and pat ourselves on the back for deriving this theory only using the dimensional analysis. But I want to show some graphical illustrations before we conclude. So of course you can show the graphical relationship between any 2 variables at a time pretty easily on an xy plane. This just shows a hypothetical relationship between flow on the y-axis and density on the x-axis. And usually the function follows a nearly parabolic shape. Some textbooks and some problems that you may come across will actually assume a parabola. I'm illustrating it here as a slightly different shape, a little bit more triangular in shape, just to emphasize the fact that the function could be of multiple forms. Just to remind you, this is the maximum flow on the y-axis. This is the maximum density on the x-axis. So when traffic is very dense, what this means is that it is not flowing. So the flow is 0 when traffic is at its most dense. So you can imagine that like a really serious traffic jam. When density is 0, that means there are 0 cars on the road. Of course, the flow is also 0. And there is a point up here where the flow reaches a maximum, and the density is somewhere in the middle between 0 and the Kmax, or sometimes this is called the jam density. And sometimes this Qmax is also called the capacity. So this is an important picture to think about. If we indicate a point on this function, so this point here we'll call it traffic state, call it traffic state 1, and it's associated with K1, so its particular density and its particular flow. So this is on the right-hand side of this curve, on the higher density side. So traffic is more dense, and the flow is somewhere in the middle between 0 and the maximum. And so that is known as a traffic state. You can connect the traffic state. See, I've drawn a triangle here. You can connect the origin of the graph to the traffic state, which forms the hypotenuse of this triangle. The height of the triangle is Q1. The base of the triangle is K1. And so remember I told you we talk about triangles. So the slope here is the rise over the run, which is Q1 divided by K1. The units of that slope are just number per time divided by number per distance. The numbers cancel out, and so the units of that slope are distance per time, which is just the speed. So for any traffic state on this QK diagram, as we call this, the slope of the line connecting the origin to the traffic state is the speed at that traffic state. So the slope of this hypotenuse is V1. I'm going to show you another quick example. Traffic state 1, as we just saw, traffic state 2. So the speed of traffic state 2 is the slope of this line. So the question here is, which traffic state is operating at a higher speed? And hopefully you can see that traffic state 2, while the two states have the same flow, they have different densities and different speeds, and actually traffic state 2, the speed is much higher. So actually this side of this diagram is referred to as the free flow regime of the diagram, so high speed, and then this side of the diagram is the congested regime with the speed decreasing from this value to 0 on the far right hand side. There's another way to look at these two parameters. This is a speed density diagram. So generally speaking, the relationship is a straight line for traffic state 1 with value V1, K1. You can actually come up with a formula that allows you to predict. So a theory, as we're talking about here, a theory of traffic flow allows you to predict one variable given another variable. In this case, the slope of the relation we'll call M, which is V sub F divided by K max. So if we want to calculate, if we know this relation, and if we know K1, we can calculate V1, which is just V sub F minus M times K1. Could be simplified, inserting the value of M. So in this case, V1 is the free flow speed times 1 minus K1 divided by K max. And so you could calculate the speed for this relationship for any value of density. Lastly, this is another, the final way that we can illustrate these two parameters. This is a speed flow diagram where speed is on the y-axis and flow is on the x-axis. You will see this later in the highway capacity manual, but this places the maximum flow or the capacity over here on the right-hand side. This is the free flow regime on the top and the congested regime on the bottom. More about that later. So I want to conclude. We do measure real traffic data, and this slide shows real data measured from a freeway corridor. And on the upper left-hand side here, we have a flow density plot. So that was the one that was kind of like a parabola. So in this particular case, there are a lot of data points over here on the left-hand side. This is the speed density diagram, which I modeled earlier as a straight line. And then this is the last one, the flow speed diagram that showed the parabola going horizontally. So this shows that real data approximates the theory, and we'll talk more about some of the pros and cons there. So in conclusion, we've discussed some basic traffic flow measures based on the idea that you can go out into the field and take some simple measurements. You could do this yourself. importance of paying attention to the units of these measures was emphasized. We used dimensional analysis to derive the fundamental theory of traffic flow. We looked at several different diagrams for illustrating that theory. And then lastly, we looked at some real data, you might call that big data, from a freeway, and briefly discussed how those matched the theoretical foundations. So thank you for your attention. This has been Traffic Flow Theory Part 1.